The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
A lot of the women in this village, about 20 of them, are part of this co-op called the Solar Women of Totogalpa. And these women basically, they get grants from different funding sources to research sustainable energy options. So one of the things that they do is they make their own solar panels, and the people in the village can buy these either with money or with hours spent like working in the co-op. So we decided that even though they're making 60-watt panels, okay, this does not match that, but even though they're making 60-watt panels like these, they also all have cell phones, but a lot of them are off the grid. So they also need ways of charging these, and we thought that solar power was a good way of doing this. So what they're doing right now to make these is, this is a poor image, but basically they take the smaller cells, which are about 8 by 15 centimeters, and these are rejects, so they're not as efficient as standard cells that we might use here, but they're much cheaper. So they use those. They by hand solder them all together, line them up, put liquid silicone over them, and then put a glass piece over it, and then encapsulate it all and make it look much nicer like the ones you saw on the previous slide. So this is like, you know, a much smaller, much nicer looking one that is made in China and imported, but it's available for $20 in Managua, which is about 3 hours from the town we stayed in. And so these are very difficult to get and they're pretty expensive, but they also would like to be able to make them there so that it's about the same price, but it's more kind of accessible, it employs some people, and is in general just more sustainable. So that's what we set out to do.
Hi. So as was mentioned, they do have access to solar cells. And so, but unfortunately what happens right now is to make the cell phone charger, they need to cut these cells. And what they do is basically they cut one of these cells into 4 parts and then attach them in series so that the voltages add up, so you can get up to 6 volts. Unfortunately, with this process, what ends up happening is you end up losing a lot of the cells just because the method that they use to cut them is not foolproof. And so you end up cracking a lot of the cells. And when we talk to them, we realize that they waste about half the cells they cut. Which means that if they needed to use 9 cells, they'd end up using 18 because they'd waste half. And so we figured that if we could somehow step up the voltage given by 3 original cells, they call these original cells. If you could step up the voltage given by 3 original cells to the required 5 volts to charge a cell phone without cutting them, it would save them a lot of time and money. And so what we decided to do was connect 3 of these cells in series, so you get a 1.5 volt output, and then have that output run through your circuit, which steps it up to 5 volts. Now, the circuit basically works like this. You have, so this is your input. You have current inputting here at 1.5 volts. It goes through your op amp that steps it up to 1.25 or 3.3, depending on how it's connected. For our purposes, we needed 5, so we connected it accordingly. These are capacitors, an inductor, and a xenodiode. The xenodiode is used to make sure that the voltage goes in one direction only. And then, so basically, these 2 leads have a voltage difference of 5 volts across them when connected to the solar panels in optimal lighting. And what we did was we surveyed what kind of cell phones they use and realized that for the most part, they're Nokias. And this is the most common type of phone that's available there. And we got the adapter that they use to charge this, cut off the port and attached it here. If you look at our prototype, you notice that, so the orange and black wires are these, basically, and then they connect to your port. And then basically the idea is that you plug it in, put it out in sunlight, and you use this as a way to make sure that you're always facing the sun optimally. But there are a lot of notches along the sides, and so basically you wedge this in, and then you can change the angle of your panel. So this is just a very rudimentary cost breakdown of what we estimate our cell phone charger to cost them. Basically, finally, this is the number that we were trying to shoot for $20, and we're slightly above that, but we figured that there are still ways to optimize costs, and that it is very viable for them to get this below $20. Yeah, basically this is just to give you an idea of how expensive all the components are. I don't want to run through each one of them,
Just to mention a really quick thing, we're also including $4 for labor.
Right.
So even though it is a little bit more expensive, it is produced locally and it is providing employment.
Right.
Whereas the China-made one, we're not providing any employment for the community.
Right, exactly. Like the China-made ones sell for $20, but like one said, they don't provide any source of income to the people in Tokugawa. Yeah, so this is just to give you an idea of the cost breakdown. This is just a blown up image of our circuit again, just to give you an idea of the components that we used. Essentially, like this circuit is enclosed by this casing right here. So it's that circuit basically underneath this.
Which you can see in this image
Which you can see in that image, the next image right there. Right, so I mean, like I said, this is your output from the solar cells, which go into your circuit and then go and charge the cell phone. And the actual circuitry, so just to talk a little about like why we made the circuit like this, we decided to use a breadboard because when we talked to Mauro, who's our community partner, who's one of the community partners there, he told us that they do have access to breadboards but don't have access to protoboards, which we were initially planning on using. And so we decided to stick with the breadboard model. And we also, we asked about the various components and they are available. The only component that we potentially see having to be shipped there is this. But since they already ship solar cells there, it would just be another added component to ship, and it's not very bulky. So we think it's definitely viable. So that's why we decided to go with the breadboard design. Apart from that, I'm just going to talk about this.
But before that, I kind of just want to speak a little bit about the design in general, why we chose to build it the way we did. First of all, it's made out of wood because it's a really locally viable material. First of all, let's talk about the solar panel. So this is the solar panel. Because we didn't have, I guess, easy access to liquid silicone and aluminum and glass, which they use, we instead use acrylic and a different method to glue the cells. In Nicaragua, they make these differently and they customize it for every application. And so when we were talking to him on the phone, he already had made some changes to the initial design we had made. And he said he would change the hinges and everything. So it would be made out of aluminum. So we decided to, originally we wanted to make leg stands so we could change the angle and notches here. But then we realized that it might be easier to put something in here instead of having to have legs. So we just came up with the notches and a small cut PCB pipe, and then you can change the angle. Moreover, we wanted to create a way to protect the circuit. So we just encased it around this aluminum frame with the two wires hanging out. Additionally, these are really easy to switch. So if you do have another cell phone, you could switch the charger and install another cell phone. And another reason why this is over here, just in case of rain. I mean, hopefully you have it outside and you'll be looking it out. So in the case of rains, this is waterproof, and it'll also protect the cell phone and the charger for at least enough time for you to come and get it. If it's raining really hard and raining sideways, then it's gonna get wet. But for the enough time, if we realize it's raining, it should be protected.
Right, and just like Juan said, so like he said, we could also have another adapter going out from the same leads. And we actually do have a USB adapter that runs at the same voltage that we did test. But but for the purpose of the demonstration, we decided to go with the Nokia just because it's the more locally available phone. So, but we could potentially have a number of different adapters shooting out from here, which all run at the same voltage.
So, so we were doing some testing in the past couple of days to see how much power we could get out of the cell phone. Using the lamp over there, we can test it. We can show you a demo of how it actually it's working, because it does work.
Do you want to actually? I don't know. I think this can stretch. Do you want to just get this?
So, here's of course, the solar panel.
Sorry, that's all right.
You can make it incident to the light. And we connected. It is charging. So it does work. You got scared for a second there. I was like, no.
Well, there's no way to stay charging. It just has the little charging
Yeah,
symbol.
Right.
So it does work. However, we wanted to see how efficient it is and how fast we would get it to actually work. We realized that Boston May sun is not the same as Nicaragua, the sun in the equator. So we conducted the test with a lot of different lights and light outputs. This is the output power of the solar panels, calculated by just measuring the current and the voltage at the same time out of the solar panel. And that's the input power, sorry. And the output power is the output power out of these two leads, calculated by measuring the current and the voltage at the same time, so we don't get any side effects. We then estimated for the efficiency, and this is for the Boston sun and the power we're getting right now. If we estimate for Nicaraguan sun, we would be getting around 65% efficiency. Right now, we're getting about 0.2 amps in Boston. I mean, yeah, right? 200, no. 0.02 amps, 20 milliamps in Boston. If we extrapolate it for what we were getting in Nicaragua with the power available in Nicaragua, we'll be getting around
80 to 100.
80 to 100 milliamps, which in the cell phone batteries are about 800.
Yeah, 800 milliamps.
800 milliamps. So it would take about 10 hours to charge a cell phone, which is not ideal because we were aiming for at the beginning was 4 to 8, 4 hours, 5 hours. We're expecting 200. The circuit said that 200 milliamps would be outputted from the circuit, but instead we're getting 9 to 100. So it's not as efficient as we would like, but it would still work. And
right, and just to explain why, so the scatter plot has a point actually above the 100% efficiency mark, which is theoretically impossible. But that was just, there was probably some kind of error.
It was one of the times we were using the actual sun, and so it probably changed a little bit in between, so.
Right.
Oh yeah, it was just yeah, that's it. Thank you very much.
That's pretty much it. If you guys have any questions.
So how did you estimate the Nicaraguan sun?
We took measurements while we were there as far as like what voltage and current output each cell was at around like 1 o'clock.
Okay.
And then extrapolated that based on what we think, how much sun that would relate to.
With the 10-hour issue, the only thing I think of is that the sun moves in
Right.
10 hours.
Yeah.
So the user would have to understand that they would have to move so it might actually be longer than 10 hours. You know, in optimal sun is 10 hours, but it might be more like
The one thing
12.
we noticed was when talking to people, they usually didn't actually charge it from completely discharged to charged. They usually charge it from about half charge, so it would be more like 5 hours, which is more reasonable because that's more like the span that the sun is usable in a day.
How long does the cell phone battery last?
We got mixed answers on that. When we did about 10 to 15 interviews with people and asked that question, and most people I think on average said they charge it about once a week. There was one person who said once every 15 days, once said like every 3 days. It just depends on how much they use it.
It also, I think, depends on how many cell phones they have in the family.
Yeah.
Because we noticed that like a certain family had one cell phone for the entire family, so it obviously drained out faster. But if you have individual cell phones, they tend to last longer because you're only, and so it really depends. But for the most part, like Liz said, I feel once a week was a very reasonable, maybe twice a week, I guess, on average. Not they don't use it a lot.
And most of them just, we noticed just from living with the families, a lot of the times the cell phone just stays at the house so that if they receive a call, so they can actually still be sort of using it while it's in charged, because they'll be within hearing shot. So if they get a call, they can unplug it and answer it, but they can't call with it while it's charging.
Right. I mean, essentially they use a lot of cell phones as landlines, just because they don't have landline connectivity. So, yeah.
So just a little bit about the community partner we worked with. They are called the SAPROSER. They're a human development NGO based in Santa Ana. They work in rural areas and try to improve the quality of life through environmental and nutritional education, also microcredit opportunities, and general community development. One of El SAPROSER's current projects is in introducing rice cultivation in El Salvador, both as a source of nutrition but also as income generation. And in order to prepare rice for consumption, it needs to be threshed and also dehusked. And current methods that the community uses are very time and money intensive. So our design challenge is to develop a cheap and local process that dehusks rice more successfully and conveniently. The most important product attributes that we focused on were the efficiency and the affordability of the product. Our goal was to make sure that more than 90% of the rice was successfully dehusked while keeping the price of the product under $2. We also looked at cost and durability and safety of the product. And so after extensive research and some brainstorming exercises, we concluded that the best approach to this design challenge is to modify an existing molino, which is a corn mill currently used in the communities. The advantages are that it's already available and it's being supplied by our community partner. And essentially what we're proposing is inserting another material between the two metal plates of the molino that would provide enough friction to dehusk the rice grains, but at the same time prevent them from being broken. And some of the challenges that we're dealing with are the lack of precision of the molino, and then also the fact that it has friction so that it wears the materials down.
So I'm going to talk about the experimentation process. So initially our first problem was to decide on what kind of insert we wanted to use. So we looked at metal, various types of rubber and foam and leather. And when we were looking at these materials, we really evaluated them on their cost, how much residue they were going to leave on the rice, how long it was going to last, so how durable and how available the material was. So when we did our experiments, our two main variables that we were looking at were essentially the type of material and also the tightness of the molino. So essentially the tightness was how much space was going to exist in between the insert and the metal plates to provide the adequate friction. And when we did our methodology, our experiments, first we inserted the material and we controlled the spacing by screwing the tab all the way in until we couldn't turn it any tighter. And then we turned it a certain number of turns back out, so we knew how much space there existed in between the insert and the spacing. And then we ran the rice through the molino, and after we ran the rice through, we winnowed it and we separated the rice into husk, when it was still husked, and if it had been dehusked or broken, or the rice particles or the leftover husks or the free particles we were left with. And these pictures show the various types of experiments we really did, and it was quite an extensive process. We experimented with various different types of materials. We would use one material and vary the number of turns. We might insert multiple layers of the material to see if that changed anything, and also we would run the material, the rice through twice and see if that changed the efficiency of the rice itself. And ultimately what we decided was that leather was the most appropriate insert for us. Because when we did different material inserts, we essentially found out that it wasn't so much the material that matters, but it was the number of turns that would change the process and the efficiency. And we knew that this material had to be soft enough so that the frictional and the torque wouldn't break the material, but we also knew it had to be very durable because we didn't want it to wear away. So leather was the best option for us.
Okay, so when we were looking at leather, we first decided that we wanted to do unattached. Without having to glue or adhere the leather to the molino, it allowed for flexibility for the molino use, and it
had pretty similar results, and it wasn't hazardous if we're not using some toxic glue. We also decided with brown organic leather, we didn't want anything that was too processed or patented or anything, and we thought that one piece might be acceptable because it was similar. We had similar results as 2 or more pieces. It's obviously cheaper if it's only one piece compared to 2, and it's less hazardous if we're not gluing or adhering it together again. So we actually were worried about toxicity after we learned that tanning was kind of chemical intensive. We concluded that there's no dangerous exposure because chromium-6 is the most hazardous chemical that's being used in treatment, and it's actually broken down into chromium-3, which is an essential nutrient in your body, so when it's inhaled, it's okay. The OSHA says that 100 micrograms of chromium per liter of drinking water is acceptable. We found that that's equivalent to eating 7 of these inserts a day, so we don't think anyone's going to do that. We also found that there's not really significant leather wear. We processed about 7.5 kilograms of rice, which is a family's monthly rice consumption, using this insert, and I don't know if it's this round, but this is a new one compared to the one that we processed. So you can tell that it's stretched a little bit, but other than that, there's no real wear that we found. So we wanted to optimize the process after we concluded that leather was our material, and so we processed about 1.5 liters at a time, and we did a whole bunch of different experiments. We really focused on the optimal tightness of the merino, and we did this by looking at the percent that was husked and the broken grains and how fast we could do 1.5 liters. And then we also attached 5 washers to the side knobs. This allowed for stability for the merino, and allowed us to better control the spacing between the metal and the leather, so we could really optimize our tightness. So this is the data from our experimentation. So we found that using the one piece of leather, we could get 94 to 96% husk, which is really good. And so our optimal outcome was one piece of leather unattached, 4 to 5 turns out. And looking at our original project specifications, we found that this was very comparable to what we had wanted, and the durability, we are positive that it will last 160 pounds, so we estimated that as our minimum. So our final conclusion is that one piece of leather unattached to the merino is the best. 4.5 to 5 turns, but the user can vary that depending on what they want as broken in versus dehusked grains. It's very minimal cost. It's about 50 cents per insert. It's durable. Again, we expect it to wear normally, but not too much, and it's not toxic.
So now that you've heard a little bit of the decisions behind the process, I just want to take a little bit through what it might look like for someone that's in the community and what they would have to do to be able to use this process. So first they would have to get a hold of a piece of leather and cut it to the donut shape that would fit into the shaft. And if the Molino body wasn't set up already, they would, put it on a stand and proceed to put the leather on the shaft and put that through the main body, and then continue by, adding the reservoir up on top as well as the handle on the side. Then the next thing would be to add these washers so that this brace can hold the shaft in the main body, but it can still be tightened enough and still leave enough space for the leather to fit inside. Then they would turn the knob all the way in, and then turn out the specified 4.5 to 5 turns, or according to their preference, whether they wanted broken rice or more unhusked rice, and would then crank away and put the rice in and process, and from there separate the husks from the grains by winnowing it using their preferred method. And from there, just as a side note, we also found that when we're doing our more detailed experiments, we found that, or to separate the broken rice versus the whole grains, we found that when we were shaking it back and forth in the sieves, the unhusked rice actually came up to the top just because it's a little bit larger, and so that sort of gave a natural separation between the ones that still had the husks on and the ones that didn't. And so from there so what we're going to be suggesting is to put the winnowed rice into a container and shake it back and forth a little bit, and from there the rice will then collect to the top and be able to sort of scoop it out, and that's what gives us our 96% efficiency, and that's the other contribution to the process. So from there, the rice is ready to go, and it would just have to be washed before it's eaten. So we'd just like to thank Asa Prosar and the D-Lab staff for helping us out, and for Will Floyd from Windmill Rice for giving us our rice. So if you guys have any questions, just thank you for listening.
That must mean we did a good job. Available this weather.
So we visited, or I guess I did. These went to
We
the.
went to a store in one of the towns nearby these communities, and it was a shoe store that just sold leather in all types of quantities. So it is available, and the community partner that we worked with, actually they were the ones who brought us there, so they would be able to supply the communities with the leather.
What fraction of your rice remained broken at the end?
It was probably about a third. I mean, what we were really concerned with was how much, like the percentage of husk to like dehusked rice, because like you can eat broken rice. It's not as like it's not as nice. You would rather not eat it, but for the most part, we would rather err on the side of dehusking most of the rice versus leaving it husked and whole. So it was probably about a third of it was probably broken. We lost maybe about like between 5 and 10% of it was like just like sand grainy size. So it's pretty good.
But it's also something that people can adjust the turns to. So if they would prefer having more husked rice and just pull it out themselves, then it would probably be less broken rice because it's not going to be as tight and not going to be crushing it as much.
And something also we learned from the community partners that currently when they currently bring it to a mill to have it dehusked, and when they get it back, some pieces do still have husks on and some pieces are broken. So it's not, what they currently have is something similar to what we're proposing.
And they could theoretically cycle the non-husk
Right.
stuff
Yeah,
back
just toss
in.
it back through.
Yeah.
That's what we found was really nice about the. We weren't quite expecting this, but when we were shaking it, well, look at that! Like all the husked rice is like right in the center. So like, okay, so we just scooped it all out. We just put it back with the rice that hasn't been processed yet.
And the sieves that you used, are those?
Yeah, so the sieves, the fact that it's a sieve is sort of irrelevant. Like we just happened to use a sieve, so yeah.
You were using the sieve to take out the broken rice.
Exactly.
Right?
Yeah, and so it would just be a
use.
fairly shallow container. So the fact that it's a sieve doesn't really it isn't the one that's causing it to.
What we
separate.
did realize though was really important that like the bottom was relatively flat and sturdy, and that the sides wouldn't bend. So you wouldn't want like a plastic container because you can't get the right motion for the shaking back and forth for it to separate. So some kind of like.
But we just actually used the same container that we were winnowing in. So we could. I mean, we don't have the huge like platters that they sort of use, but that would definitely be something that we'll suggest to Asa Prosar and have them try it out to see if it works.
Good afternoon, everyone. Thank you for coming. Our group project is Barrel on Fire, Charcoal Desire. My name is Jessica Artiles, and along with Vivian Dean and Curtis Wool, we went to Sabana Grande in Nicaragua, and we reintroduced and rehelped the women make charcoal out of agri-waste. So for context of charcoal in the community of Sabana Grande, in about 2009, our professor Amy Banzar visited the community and introduced charcoal. Over the years, the knowledge was lost. The women lost practice, they had challenges, they didn't yield briquettes. When they tried to make it, they were getting less than 10 briquettes per yield. So we went this spring break to Nicaragua. We reintroduced the process to 4 women, whom we now call the charcoal captains. And when we were there, our yield of burns were coming up to around 80 briquettes per burn. Since then, we came back, we redesigned the charcoal making process, we made the innovations, sent them back our feedback and results. And when they've done it with our new designs, they're getting up to 110 briquettes per burn. So the project is looking commercially viable for them. They're looking at making the charcoal for the restaurant that's on site to fuel and to cook with. They're going to be making charcoal to sell to the community, and they're actually going to be displaying it in their community fair this mid-May on how to make charcoal and how to sell it.
So the way that we identified the problem was looking at the current charcoal burning process. It requires lighting this oil drum on fire which is packed with dry biomass, and then sealing both the bottom and the top. So this process right now, with the barrel standing on top of the 3 bricks, is optimized for cost. So this is the most low-cost way to do it. However, we felt like we could add improvements that would be justified in their cost, because this has 2 main problems. One is the issue of heat exposure. So the user actually has to get quite close to the barrel to be able to kick out the bricks from the bottom. And the second is the safety issue, where where in sealing the bottom of the barrel, you have to tip it, and this could result in some accidents. Oops. So as you can see, there are flames coming out of the bottom of the barrel as they're doing this, so that's the heat problem. And then as they're tipping it, the barrel fell over and almost landed on one of the women. So this is a safety concern, and there was also a lot of biomass to the left of the barrel, so it could have lit all of that on fire too.
Right. So how do we solve this? Our solution consists of a circular dugout that is slightly smaller in circumference than the barrel. And within that dugout stems 3 air channels, and within each air channel is are 2 bricks that are embedded, and the barrel simply sits on top of the ground and on top of the bricks for like a very stable setup. When we tested our solution, we wanted to make sure that the biomass could still be lit pretty easily through the bottom. And what we found was that biomass is actually, it's a lot easier because the air channels actually block any wind that could interfere with the process. We also calculated the size that the air channels needed to be to allow the necessary airflow for a very thorough burn. You can see on the sides that the barrel is sealed to the ground except for by the air channels. And because the barrel sits on the ground level, we eliminate the risk of having to tip over the barrel or having to handle or move the barrel while it's on fire. Eventually, you'll need to cut off the air supply to the burnt biomass to allow it to carbonize. And so the way we figured we would seal these air channels is through these metal plates. So the idea behind these plates is for the user to be able to slide the metal plate from a distance, keeping a safe distance so that they're not exposed to the heat as much. And through several design iterations, this is our final design we came up with. It's, you can check it out. It's made of one piece of sheet metal, which is very readily available in Nicaragua. And the handle is made by making slits in the sheet metal and curving it around and riveting it to connect at the top. And riveting is very available in Nicaragua as well. So yeah, we just use metal shears to cut the sheet metal, so it's pretty simple. We have a video of Kurt demonstrating the use of these new metal seals.
All right, I'm filming.
So you can see he does this pretty easily, maintains a safe distance, and it's pretty quick.
Go for it, go for it. Please.
And that is our solution. A big question that came up when sealing the barrel was whether or not we should seal the bottom first or the top first. And we found through experimentation that it was easiest to first seal using metal seals, so we cut off airflow so the flames aren't as intense coming out of the top. And then you can throw on the lid on the top, and then that allows for smoke to come out of any air gaps or air holes, so you know where exactly to plug sand in. So that's our solution. We actually delivered this to the Mujeres Solares, and Jessica will tell you about the feedback we got.
So our group is unique in that we are able to have a native speaker, me, communicate with the women constantly. We kept communication with them through emails, phone calls to their cell phones, to various women and men on site. And so this is a picture of when they did their own barrel dugout. Again, we had our design and we submitted it to them on, a document of here's what you should do, new and innovative. And so they did the barrel dugout and they tried it. They made their own sheet metal designs to cover the barrel. So we only sent pictures of ours, but they went ahead and they said, we're already going to make another design iteration. We love the idea. We asked them questions about, how do you feel about the safety risk? And they said, there's no risk of the barrel falling over now, which was just as important as the heat. We asked them, how do you like cooking with the charcoal now? And they said, I cook tortillas, which is one of their most valued foods. And they said, with the charcoal we made, the tortillas were delicious. I made arroz con leche with the charcoal. They're going to be using arroz con leche is like a rice pudding. They're going to be using the charcoal now that they feel safe enough to continue to use it. They're going to be using it in the community fair this mid-May. And lighting the biomass was also an added advantage because it was very fast. They all had to do was align the bottom of the holes on the bottom of the barrel with the air channels. And now when they went to light it, it was easier to light because it was wind protection. So in conclusion, in summary, we've taken the charcoal making process and added 4 points of making it easier. 4 innovative points to the process. We've made the lighting of the barrel easier because now when you're getting the match under the barrel, it's wind protected so the wind won't put it out. Now while the barrel is burning for those 15, sometimes 25 minutes, it's cooler. The flames aren't coming out from under the bottom radially out towards your feet. Now the sealing of the barrel is safer because there's no longer a tip and kick method. All you gotta do is use the metal sheets. And it's faster to seal as well because it doesn't require coordination and all you gotta do is slip the metal sheet like you saw in our video.
So throughout the process of developing the solution, we did some experiments around where the heat was coming from, and we discovered that most of it was coming from thermal radiation from the barrel. So we thought, okay, a way that we could improve our solution even more is to develop radiation shields. And the kind of the gold standard of radiation shields is aluminum tinfoil, but we ruled this out because it is just too brittle and wouldn't be able to withstand the thermal cycles of a barrel burning again and again. So we experimented with 2 others as well. Here you have like window screening. This is made out of aluminum, and galvanized steel, like metal mesh. And the conclusion was that it wouldn't justify the cost. The heat reduction wouldn't justify the cost. So what you see in this graph is the cost of insulation going up on the x-axis, and that's as measured by more and more layers of either the metal sheet or the window screen. And on the y-axis, you have percentage of heat reduction. So you do see a positive correlation. The more of that insulation that you see or that you put on, the more heat reduction you get. However, spending upwards of $15 doesn't even get you 40% reduction in heat. So where does this leave our solution? Well, we think that the dugout and metal play seals really represent kind of a sweet spot, like in a range of solutions. At the very top, you just have the tip and kick method, and then you can introduce the dugout and just seal the holes with sand, but that wouldn't give you as much heat reduction. And ours is medium cost. The sheet metal is not that expensive to make the plates out of, and it gets you a significant heat reduction. And finally, adding some kind of radiation shields is pretty high cost, but gives you more reduction in heat, but we don't think that it really justifies the cost. So we have a lot of people to thank. I won't read them all out, because I think we are just about done. But we are looking forward to your questions and any feedback you might have.
Do you have an estimate on how much each metal sheet would cost and how long you think it would last?
That's a great question. We thought about that a lot, but when we introduced, so we don't, but when we introduced the sheet metal, they said, sure, we'll do it. And again, they made one set of this design of a sheet metal, and they're ready to make another set with another batch of supplies to make another set of sheet metals. So it doesn't seem like it's a restrictive cost for them.
Yeah. That is one thing that we neglected to look into. But we know it's there on site because they use this type of sheet metal for their solar ovens. So we know they can obtain it.
And I don't think they had to go out and buy it for anything because they already had it in their center. So our case is kind of special in that they do have these resources. So.
It seems like the topping method still involves getting close to the barrel, where everything else you maintain the distance from the barrel. Have you considered just riveting a small handle on top of the top piece so that you could also put that on with your stick?
That's really interesting. They actually, in the design that the women made, That's a good question, by the way. In the design that the women made in Nicaragua, they put a handle on their metal sheet, and they said that for our second iteration that they're gonna make, they're gonna take out the handle because they realize it's unnecessary. They said it's not that hot. You can get close to it and just insert it with your hand. That's what they're doing. So theirs doesn't even have the little hole or the lift handle that we've made for our designs. So they're okay even without a handle.
Wait, I think you were talking about the top, right?
Yeah.
Yeah, they have one where it's like the circular metal plate that we have here, and there's like basically like a pot handle over it, and
So
they
you use
just
a
stick the
stick.
stick.
Yeah, I think they use a stick.
Put it over, so they have that.
Okay, we are tight on time, so I'm gonna cancel questions.
Okay.
Thank you very much, guys.
Well, you know where to find us if
Yeah,
you have any more.
we're in the corner, so come ask us questions. Thank you.
Thanks.
For coming. We're Team OJ. I'd first like to introduce the team. I'm Bob Myron.
Brianna Conrad.
I'm Emily Rosser.
And Carter Chang.
So our project is sealing a plastic bag sealer that we developed during our trip down to Nicaragua over spring break, where we were fact finding and analyzing 4 different projects that we were looking at, and we chose to develop this one for the remainder of the semester for a variety of reasons. First, I'd like to describe the situation we found in El Revoir, which is the community that we visited in Nicaragua. They have a large orange crop that they get twice a year, and it's very imaginable that every similar community has that same orange crop, so they can't really sell those oranges on any type of market because the market's flooded. So the goal is to basically develop a way for them to preserve that orange product, and for us it's in the form of juice, so they can sell when there is a market for oranges. We presented, this project was first developed in last year's class, and we presented that version in El Revoir to the women of the community who will be using this product. And the presentation, though we had some technical difficulties because we went down expecting to be able to run the device off of a 12-volt car battery. But when we got there, we realized that since the last group had gone down last spring break, they had just installed a micro hydro grid, and they now had 120 volts AC coming out of a wall socket. And so nobody really had 12-volt car batteries for us to power the device. So we strung up a bunch of AA and AAA batteries to be able to do a couple bag seals. And there was a lot of excitement about this device while we were down there. You can see them we gathered around, and but we can only do a couple bag sealers for the AA batteries that we just happen to have in our backpacks, or totally drained. That's basically the gist of the project, to be able to create something that they can use in this community and also be adapted to other communities so that they can seal these orange juice or whatever kind of thing they're trying to preserve in the community. And they have a pasteurization process that comes before this bag sealing that they use. So this bag sealing is the second step of that process. And we work with Also Phoenix, which is a Nicaraguan NGO. They do sustainable development and energy work with many rural communities in the area, and I'll pass off the roster.
Okay, so Also Phoenix, we're incredibly grateful for and helped us out a lot. However, they rendered the first prototype obsolete. So we had a couple improvements to make after this. This was the first version. As you can see, a kind of prominent circuit that they was prefabricated, the most expensive part of the entire device, a hinge that they had bought, and a latch that was kind of sticky to pull. Therefore, we wanted to kind of remedy this in version 2.0. We also wanted to kind of incorporate a few of the things that we learned in Nicaragua. That there is not really a reliable power source. We wanted to meet both DC and AC needs. To do this, we hooked up we got a adapter that can go from the wall outlet, or wall AC power, and output 12 DC volts. Also, you could just take those same leads and hook them up to a 12 DC volt battery and achieve the same effect. Second off was this pasteurization process. We didn't really know much about it for the initial prototype, but after going to El Revoir, we did learn that the pasteurization process is there. We just have to get the oxygen out. So we, had these two parameters in place while we were trying to think of a design. So, air removal process, getting all the air out, and ergonomics were also factors in the design, and this would lead to us kind of exploring several different orientations. First off, a vertical sealer, whether it was hanging off from the edge of a table or just mounted like that. It wasn't really conducive to user friendliness. You had to hold the bag in place. It was kind of difficult to get a clean seal without any air in it. It wasn't really the best. Next, a handheld device, kind of like a clamp that you could just put in place on the hanging bag. It had a lot of moving parts. We felt it wouldn't be the easiest thing to scrounge for those parts in Nicaragua. It was, kind of a lot of fabrication involved. Last but not least, we had a horizontal sealer, most similar to version 1.0, the prototype last year. Our biggest problem with this was, A, it was messy. It got orange juice that was running off everywhere, and it was harder to get a airtight seal as a result. Also, just ergonomics, pressing on it again and again and again was kind of difficult. So, in order to kind of make the best of both worlds, we decided to combine both vertical sealing and horizontal sealing, the two most feasible, and put it at 45 degrees. Perfect split of the options. Anyway, so this is the CAD model of our design. The reason we wanted to put it at 45 degrees was to allow kind of a path for the runoff to go into a bowl underneath, hence also why it's elevated. Also, it's kind of easier to smooth out the bag and get all the air out when you're doing this. A lot easier to kind of chop at the water level, or put the arm down at the water level and get all the air out. So, with this design in mind, we eventually led to
our final product. So this is, as you can see, our final product. We decided on the 45-degree angle for usability and just for functionality. One of our great improvements is the latch. So originally the latch was a wire that was hanging out that people would have to manually pull with a significant amount of force. But in this orientation, we have a easy spring-held latch where all you have to do is quick light push and it opens the OJ sealer. And another improvement is the circuitry.
So first of all, I'm going to talk about the power adapter. As you can see, we just bought a plug into the wall power adapter. We did look into making our own or running things without bringing the power down, but we found that this was by far the simplest option and comparable in price to any others. So we ended up going with the buying a pre-made one. The circuit in the previous design was very expensive. It was a pre-made timing board, and one of the places that the other team had actually thought of as place for improvement was to design a separate timing circuit. So we did that. We've put it on the side here so that the LED is visible. It's just a LM555 timer, if anyone's familiar with those, and the circuitry to make it so that we can change the time from about 3 seconds to about 30 seconds for different temperatures of juice and thicknesses of plastic and stuff. So the wheel for changing it is actually in there. So you would set it, get it right for one day, and then put it back up. And you turn it on by hitting a button that sets off the timer. There's a light here that would go on. We've actually got it so the timer turns on the nichrome heating element for a certain amount of time, which melts the bag, and then the LED will stay on for about 5 seconds after the nichrome heat has turned off, because waiting 5 seconds is good so that the plastic isn't still partly melted when you're trying to pick it up, and so you don't burn yourself. And we found that counting it on your own was very difficult, especially if you're excited about sealing your first bags of juice and stuff. So we made the LED stay on longer to give it very clear, this is when you take it out.
Looking at the cost of our product, originally the version 1.0 cost about $56 for all the materials. We were able to cut that in half with the additional functionality of our product. We were able to ensure the airtight seal, in addition to have a very usable latch system, in addition to a great timing circuit that's compatible with their AC power down there. In addition to that, in terms of implementation, we plan to deliver our product to Austin Phoenix via Amy in August, I believe. We'll bring the product down there. In addition to that, we will have a user manual in English and Spanish with user specs, in addition to additional circuits just in case any repairs. And then also things will help distribute it to the end users. We'd like to thank also Phoenix, our mentor Ken, Amy, Amit, D-Lab, MIT, as well as the Microsoft Nerd Center for allowing us to use their venues. Are there any questions?
Do you have bags? Can you see them?
Yeah.
Yeah,
Would you like to
certainly.
If we can get a, oh, sweet.
This nerd center is incredible.
They have everything. Let's move their awesome electronics a little farther. There we go.
This is the messy start. Actually, someone else been terrible at pouring this.
This is our homemade Nicaraguan orange juice, flown in fresh this morning. Yeah, right.
Shots.
Anyway.
So we have the OJ in the bag. We want to put a bowl here just in case there's excess spill.
So we have this wire that's, obviously we're not using all of the heating capacity because we don't know what size of bags that they'll actually use. They could be doing personal size bags that they sell on buses or other similar situations, or they could be making kind of like more wholesale liter size bags that they sell to restaurants or something. So that's the reason for
So we have the long Nicrom wire. Place the bag here. We have a little guiding arm, so this lever doesn't, or this arm doesn't jiggle back and forth. So we create an airtight seal by sealing through the juice. Press it down here, let the excess juice come out into the bowl. And you press the button, LED goes on, and we just wait for it to tell us when it's ready.
So we've adjusted the timing because we've been playing with these bags all day. The idea being that you won't have to adjust it if you're doing kind of large batches of bagging your juice.
We haven't adjusted it since we left MIT this morning.
Yeah, it's been completely fine.
So once the LED goes off.
Yeah, the potentiometer is inside that housing though, so it's
There's the
water.
seal, and there's the bag of orange juice. Airtight. Toss it around.
Where do the bags come from?
So they're bags, the plastic bags that we found, they're similar thickness to the bags that were provided to us by also Phoenix and by the community partner, or the community in El Roblar.
In
they buy them in
Nicaragua,
bulk.
you can purchase
Yeah.
you purchase long tubes and you would seal up the bottom and then put the juice in it and seal the top.
So they would seal the bottom using this?
Yes.
Yes. So, or even just sheet plastic if that's all you
Seal,
have.
seal all four sides.
We made some bags.
And how long, how many bags do you have to go through in the adjustment process to get it tuned?
I think I did about 3 seals this morning to get it set up right. And that was.
And you could do that with water theoretically.
Exactly.
You could do that with water.
Yeah.
I mean, it was this morning we discovered that the temperature of the juice, we had like fresh from the store juice and it was all cold. That added about 5 seconds to the time. So yeah,
Yeah.
it took us 3 tries.
So there are a couple of variables you have to juggle. There's the thickness of the plastic, the temperature of the liquid inside. Also, we found really pulpy juice, kind of adds to the time as well. Hopefully they wouldn't waste too much plastic in the process. What we eventually ended up doing was kind of making a seal, seeing if it worked. If it's nope, pull it down an inch, make another seal, see if it works. So we didn't waste that much plastic overall.
Yeah, it was like 3 seals on one bag.
On one bag, yeah. Right.
Mhm. So there was one bag that was like not as pretty but still functional.
How are you protecting the circuitry?
So we have it, we used a silicone-based adhesive around the base. We add that adhesive around we add that adhesive around the LEDs and the switch.
That's an ABC pipe.
On a PVC pipe that's been spray painted.
And a hose clamp and cap. We've got it loose right now so we can probably pull it off, but the idea would be to tighten it down.
And you just put a flathead screwdriver on it and then tighten it. So it's watertight. You can pour water on it.
Yeah, we decided on using PVC since that was actually one of the most cheap components, or one of the cheapest components we encountered in hardware stores in Nicaragua. It was something like 2 cents for PVC connectors, and I'm sure pipe is equally cheap. So, yeah, just keeping the local materials in mind.
And is the idea they would make the circuitry themselves, or?
People in communities probably wouldn't. SO Phoenix has an electrical engineer who could probably make more or figure out the best way for it to be made in Nicaragua.
We have a circuit diagram that we could send them as well, and that would be sent to them.
Be part of the user manual.
Is there any safety of it to make it so you won't burn yourself by the electrical program?
next to the main plug, or does it get locked? So I guess the hope is that you wouldn't plug it in until you're ready to use it, and then you would follow the light cues. But I guess if you're moving it around and you do press the button accidentally, it would go on.
The nice thing is that, when it's pressed in place, it's pretty much completely sealed. And this is Teflon tape, and the nichrome wire itself pulls off pretty easily. Teflon tape doesn't pull heat at all. We've kind of been touching this all day right after we've been sealing.
And you can easily hold this down and hold this like with a firm grip while it's on, and still you won't feel.
Yeah.
Not that you need to seal it.
Yeah.
If it does get turned on accidentally, if you were touching it while it got turned on, it takes a couple seconds to get to temperature, so you notice it beforehand, but there's not any way, it doesn't turn on if the arm is closed or anything. It would be a possible improvement. If the arm is open for it to not turn on.
If they wanted to connect it to a 12-volt DC battery, what would they do?
We've got these today for simplicity strung together, but you just take these two leads and instead of attaching them to wires out of an adapter, attach them to clips to a battery.